Hi, welcome back to part 3 of concavity. Like going to the dentist. I am with cavity. So for question number 2, we can get a little bit triggylicious with it. This is going to be much easier second derivative than number 3. Remember that one? So when we take our first derivative, we're going to get 1 minus 2 sine of x. Taking the second derivative, we get just negative 2 cosine of x. So finding our possible points of inflection, identified as. These are possible. Now the reason why they're not called points of inflection, they're called possibilities, is because they may not work. For example, you might recall from number 3 here, negative 1 did not turn out to be a point of inflection. It's only possible because it may not. Because for a point of inflection to occur, it has to change concavity, and over here it didn't. So to do this, we're going to take our second derivative, set equal to 0, or take our second derivative, find out where it does not exist. Where does this equal 0? Negative 2 cosine of x equals 0, or where cosine of x is 0. Where does the second derivative not exist? Nowhere. So where's cosine of x equals 0? Pi over 2, 3 pi over 2 in your domain. And then we're just going to do our sign chart. We are restricting our domain from 0 to 2 pi, my favorite mathematical repper. Where's our second derivative? Which is just negative 2 cosine of x. And how does it make my function look? So I look at my two critical numbers, pi over 2, 3 pi over 2. Now we talked about triggylicious functions before. Cosine curve, the slopes alternate signs. So if I look in the middle between pi over 2 and 3 pi over 2, I know pi is there. So if I plug pi in, that becomes negative 2, and the cosine of pi is negative 1. Well, that's positive. So that's telling me over here, in here, it's concave up. So what's happening on the other side? Well, if this is concave up here, the signs have to change. Here we're going to be concave down. Change on the other side, negative, also concave down. So remember, trig functions tend to want alternate signs, unless there's some sort of multiplicity there. So we can now answer, this function is concave up on the domain, pi over 2 to 3 pi over 2, and that is because the second derivative is positive. We are concave down on the domain 0 to pi over 2, or 3 pi over 2 to 2 pi, and that is because the second derivative is less than 0. So do we have any points of inflection? At pi over 2, we went from concave down to concave up. Concave down is negative. Concave down is like your up downward facing parabola. My favorite yoga position, by the way. So we have a point of inflection, POI, at x equals pi over 2 and 3 pi over 2. There's actually 2 of them. Here we go from concave up to concave down. You can see it. That's why these sign charts are so important for us. And that is because the second derivative changes signs. And there's our answers. Alright, the last one talks a little bit more about points of inflection. This is where the second derivative is 0, but mainly where it changes signs. Because this could be a d and e, so we don't really do focus on that. This is called a POI. So let's go and find the points of inflection for here. So if we take our first derivative, that's just 4x cubed minus 12x squared. Take our second derivative with respect to x, to be 12x squared minus 24x. So to find the possible points of inflection, take that second derivative, set equal to 0, or the second derivative to d and e. Nowhere will equal d and e. Let's take a look over here. So let's see here. I'm going back up to 12x, and I'm going to get x minus 2 equals 0. So I get 0 and 2. So if I do my sign chart, second derivative, 0 and 2. Remember, my second derivative is really this 12x times this x minus 2. So if I pick a number before 0, like let's say negative 1, I get a negative and a negative. So I get 2 negatives, and that makes a positive, concave up. Between 0 and 2, I'll pick 1, positive and a negative. That's a negative, concave down. X equals 3, something bigger than 2, positive, positive, which is a positive. Concave down, concave up, terrible to me. So we have points of inflection, not possible anymore, points of inflection at x equals 0 and 2, and that is because the second derivative changes signs. And there's our answers right there. Now, I do want to talk a little bit more about asymptotes, points of inflection, and vertical asymptotes. So let's say we have a function right here. Let's say we have a graph. And we have a vertical asymptote like at x equals 1. So here I have a function right here, and here I have a function. Now this confuses a lot of students. If we were to look at the second derivative, let's say this is at x equals 1. At x equals 1, before x equals 1, notice this graph is concave up. So it's positive. After 1, this is concave down. Negative. Now the question is there a POI at x equals 1? And that's the question people always want to ask. And the answer is no. And the reason for that is what POI stands for. Remember, the P in POI stands for point. There is no point. This is a vertical asymptote. And the reason for it is no, and that's because x equals 1 is a vertical asymptote, not a point. And that's very big on the AP. You've seen that on the AP past couple of years there, where they give you a vertical asymptote and they're looking for points of inflection in some of the graphs. Anyways, I hope you enjoyed the videos. Take these notes. I hope to see you guys later. Bye-bye.